In this video, we're going to go through Beer's Law. Don't get too excited. It has nothing to do with alcohol. So the question that we're going to be answering is, how can Beer's Law be used to determine the concentration of an unknown solution? All right, so let's go through the purpose of Beer's Law. So we can use Beer's Law to determine the concentration of an unknown solution by measuring light absorption. So we're going to use a special piece of equipment where a light will be shined through a solution, and we're going to detect how much light makes it to the other side. Some of the light will be absorbed by the solution, and some is going to be transmitted to our detector on the other side. So the absorption, what the detector reads, is based on the concentration of the solution, so darker solutions, more concentrated, and the path length. So that is, how long does the light have to travel in the solution? Okay, and we express that mathematically with Beer's Law. So this is Beer's Law. A equals epsilon LC. Our absorbance is our capital A, and absorbance is unitless. Our E is or epsilon is our molar absorptivity coefficient, and that is essentially our slope, as you will see when we get into looking at our data. L is the path length of our sample, and when we're talking about path length, that is usually 1 centimeter. And then C is the concentration of the solution, which is going to be units of molarity. All right, so what's the difference between absorbance and transmittance? Okay, so transmittance is how much light goes through our solution. Absorbance is the amount of light absorbed by the solution. So as our absorbance increases, transmittance decreases. So as more of that light is absorbed by our solution, the less light will pass through the solution and reach our detector on the other side. So as I just mentioned, more concentration absorbs more light, so less light is going to pass through. And then the other important piece is that a solution with a longer path length will absorb more light because the light has a greater distance to travel. So if you've ever been underwater in a swimming pool, you can see your hand up close, but if you try to look across the swimming pool, it's very difficult. It starts to cloud up, and you can't see across the swimming pool usually because the light has more distance that it needs to travel. Okay, so let's look at an example. So this is data that we've collected in a lab. We have a solution, and we have known concentrations and corresponding absorbance values. And it says, determine the concentration of the unknown. So the first thing that we're going to do is we are going to find the slope. Okay, so when we collect our data, we're going to get a bunch of values, but our absorbance is going to be on our y-axis, and our concentration is going to be on our x-axis. And then the slope is going to be our epsilon, our molar absorptivity coefficient. Okay? So slope is rise over 1, or y over x. Our y in this case is A, and our x is our concentration, or C. Okay? And then if you're solving for slope, it would be y2 minus y1 over x2 minus x1. So if we just substitute in our absorbance and our concentration, it would be A2 minus A1 over C2 minus C1. So if we go up to our data table, I can pick really any 2 points because this should be mostly linear. So I'm going to pick my first and my last points. So my absorbance of 0.75 minus my starting absorbance. So I'm looking at these two values, so 0.75 and 0.15. Over my concentrations. So those would be 0.05 and 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. 0.01. calculator. So we've got on our top, we have 0.75 minus 0.15. And then in our denominator, we have 0.05 minus 0.01. So I get 15 as my coefficient here. Okay. So let's go back to Beer's law. So my path length here is going to be 1. So L is going to be 1, and anything times 1 will just give you that thing. So if I rearrange my equation to find concentration, concentration is going to be equal to my absorbance divided by my molar absorptivity. So if my absorbance is 0.525, and my molar absorptivity value is 15, what would my concentration be? Well, let's plug this into our calculator. So 0.525 divided by 15 gives us 0.035. Now let's go back up and look at our data table. So 0.035 falls between these two values right here. So if you notice, the absorbance for 0.04 was 0.61, which is greater than our number. And then our concentration of 0.03 had an absorbance of 0.45, which is less than our number. So our answer makes sense because it fits right between those two values right there. Okay, so that's how we use Beer's law to find our concentration. So when we're using Beer's law, we would collect this data in the lab to create what's called a calibration curve. And to solve for our E. Once we have our E, or our slope, I can pick any concentration, even ones that I didn't measure in the lab, or I'm sorry, I can pick an unknown concentration, and I can measure its absorbance in the lab, and then using my epsilon value, it will tell me what the concentration is. So I don't need to know what the concentration is, I can just measure how much light passes through it, and it will tell me the concentration. So that's what Beer's law does.